Welcome everyone. This is ALCF AI for Science training program. And this is the second session that we have within this program. Last one was devoted to how to use Theta G for AI research. The video to go and see that presentation is available now in the project website. So you are most welcome to go and follow that tutorial offline. Today we have Logan Ward, who's going to be talking about machine learning. So Logan, we are happy that you are here with us today. Please take it away.
Yeah, thank you, Elio, or Eliu. So I'll get my screen share functioning. Okay, does everyone see PowerPoint now?
Yes.
All right, awesome. So as Elio mentioned, today I'm going to be talking you all through kind of the basics of machine learning, in particular with a focus of how we can take a scientific problem, be able to adapt it into a way that works with machine learning, identifying the right approach for us to be able to take that data and learn a function from it. And then finally, and one of the areas that I think is really advantageous to learn as someone who practices machine learning in the science, how you can test it in a way to ensure that it works. So we're going to cover a lot of the foundational theory behind machine learning, but also with a big focus on how you can use a very common tool within machine learning and science, Scikitlearn, as well as be able to use more advanced techniques that leverage GPUs and advanced computing resources like we find at the ALCF. So before we jump into that technical detail, I'll just give a little bit of background on myself. So I'm an assistant scientist in the data science division at Argonne, and I joined Argonne about 4 years ago after finishing my PhD in materials engineering, where as a PhD student, I studied how we could use machine learning to solve challenges in materials science. So you'll notice that a lot of the examples here are going to be reflective of my background in materials engineering, but I've hoped to phrase them in a way that will be approachable to you no matter which kind of background you're coming from. So the thing that I like to start off with when teaching people machine learning is to indicate to them that they've actually already done machine learning before. In this screenshot that I took this morning from Microsoft Excel is no doubtly familiar to at least a large majority of you, where you can take some data and be able to learn some relation from it. And if I were to couch this in terms that made it sound less trivial, we can point out that the screenshot here is showing the training data that I was using, the model form that I applied for machine learning, as well as an accuracy metric. And these three terms here are things that you're likely already very familiar with. The idea that when I'm looking to fit a model to data, I've got to take good care about figuring out which model form I need to test to make sure it works well. And all of this is requisite on being able to devise training data. So at this point at slide 3, we've already covered about half of what you need to know for understanding what machine learning is and actually the basics of how to use it. Now, the rest of this talk is going to go into where are all the gaps? Why isn't linear regression the only technique that we need to use? Why is Microsoft Excel not the default tool for building machine learning models? And going into the details about what are really those common practices for how we use machine learning in the sciences. So another concept I want to connect to machine learning before we dive into really the details of the theory behind it is that it's in very many ways similar to the kind of semi-empirical models that one encounters across many areas of science. Now, these semi-empirical models are generally characterized as equations that people have come up with that model some kind of physical behavior, like the equation for gravity, where I know that the gravitational force is going to be equal to the masses of the particles multiplied together, divided by their distance apart, multiplied by some known constant. Now, Gravity perhaps is not a great example since it's one that's built on a lot of underlying theory, but it illustrates this idea that I came up with a physical relationship that defines the world, and I fit some of the unknown terms, perhaps the gravitational constant, to data. And then once I have that model, I can solve a lot more complicated problems. Now, machine learning shares a lot of these traits. I'm fitting data to some observations of the real world. I take that model and use it to solve another problem. But really where it's different is in terms of scale. That instead of thinking about an equation that has specific terms that I want to fit, that each individually have meaning, machine learning is more about composing a model form, some architecture that can learn from that data, because this has to deal with complexity. If I look at even a complicated model from the materials science, this the Tirschoff model, for those who aren't already familiar, is a way that we describe bonding in materials like silicon. It's got 12 parameters in it, most of which have a very precise physical meaning behind them. In contrast, a machine learning model that's used to model a very similar problem, bonding in silicon, has over 300 parameters. So when you think about being able to build this model and correct it, to be able to improve it, to be more accurate, with a semi-empirical model, you can rationalize about what is the physics that I'm perhaps missing in this model, and how do I go about in adding it. In machine learning, however, you need to think more about how do I change the algorithm that I use to come up with this model, less than being able to look at individual components. Additionally, you may be familiar with the kind of empirical models that you'll find off science, where instead of having a very rigorously defined formula based on mathematical understanding of the problem, you have something that's simple and fit to data such as you can understand the physics. Now, my favorite example coming from background in metallurgy, or the massive numbers of equations we have when designing metal alloys to say, figure out what temperatures we need to heat them in order to give them the right behavior. And here I can look at this equation and be able to understand that, well, carbon and nitrogen behave very similarly, hence why they're captured together. Manganese has a much stronger or a much weaker effect on this particular behavior. You could do very similar kinds of empiricism with machine learning, where often the divider between looking at this very conventional method of a very simple linear form that's easy to interpret, machine learning algorithms let you come up with, again, a more complex behavior that puts off more of the understanding onto humans. In this example I show on the left here, and let me get my laser pointer, illustrates some work that came out of a group in Berlin that studied how you could divide different types of materials between those that are metallic and those that are covalently bonded. And they're able to take these equations and understand a little bit about how materials bond. But again, these functional forms are more complicated because they derive from a much more complex type of learning mechanism. So at that point, hopefully that gives you some insight on, one, why we have such an expansive series on teaching you the methods behind AI and science, and in particular, why we have a 2-hour block today for learning the basics of machine learning. And that is, in particular, that the kind of tools that you needed for success in using AI are different than those that you may have picked up in other aspects of science and engineering. In particular, there are a lot of complex algorithms that not only do you need to understand their behavior in order to use them successfully, but also you have to use them very carefully, because models can sometimes have hidden blind spots. One particularly interesting example of this is work in image classification, where they show that you can take an image and apply very small, seemingly random data to it and change the overall behavior. Now, there's been a lot of science since its original paper in 2015 that have illustrated how you can design neural networks that are more resistant to this kind of what's termed an adversarial attack. Additionally, machine learning uses a lot of tools that you may not have employed in your own mathematics or computer science classes before. So we need a specific series of tutorials that are going to cover these particular kinds of tools like TensorFlow, which we're not going to cover today, but Scikit-Learn and Pandas, which we'll be getting kind of a brief crash course into. So with that overall context, we'll get started on getting into the actual content for today. And really to place the context, the two goals that I want you guys to understand today are what are the key algorithms in machine learning and how do I go about using them? And then finally, if I have a scientific problem, how I can start thinking about it in a way that I can easily identify what sort of machine learning models to use and how to test them to make sure they work. So at this point, we're done with the introduction and the level setting on kind of what it is that I think is important for you to take away from this lecture. And we'll start getting into what are the algorithms that define a machine learning problem, and then later, how can we use them? So in my view, all machine learning algorithms have roughly the same parts. They're defined by some learning function, which takes in training data that describes some behavior you want to replicate and processes on that data to produce a model, or more generally, you can think software that this machine learning model creates. And once it's defined, can be able to perform some task. Now, those are in very wide standards, and there are very broad terms. And when I start thinking about what makes each of these algorithms different, when I can think about it in terms of what sorts of different training data does it take? What do I know about each piece of data? What form does it take? And do I know anything about it? Say, if it's an image, do I know what category that image comes from? Is it a car or a cat? Additionally, the kinds of learning functions also have very different objective functions. What is it that this learning function is trying to achieve? What makes the software that it produces better? And then finally, how does it go about changing the software such that it performs better by that objective function? And then finally, these learning algorithms can produce a broad variety of different kinds of machine learning models that take different forms both on what does that underlying function look like and what are the individual weights that change its behavior. So that's a lot of theory. We'll start talking now about some of the few key examples that help you understand and be able to picture these different components. The first of which is we can take a look at the overall categories of machine learning that are defined by perhaps what is it we know about the training data and what is it we need from the learning functions. There are techniques that incidentally we'll be covering today called supervised learning, where our goal is to be able to take some entries, observations that we have about the world and what we know about them, labels, and be able to find some function that maps that observation to the outcome or the label. So in effect, like our linear regression example that we started off with today, being able to learn some function that predicts y given x. And there are many different ways of doing this that we'll get into shortly. There are also different kinds of learning problems that we're not going to directly talk about today, such as clustering techniques, where my machine learning algorithm is given just different instances of data, and it wants to find different subsets of them. Say if I gave it an image of the night sky, what a clustering algorithm would do is find that there's certain pixels within each of those images that define, say, unique groupings like galaxies or individual stars or nebula. Clustering algorithms are what be able to take those data where we don't have any labels about what makes them different and recover it. And then finally, one technique which we will use in some of our later examples today are dimensionality reduction, where I want to be able to learn some simple description of data that I have. Say, instead of having something that requires an entire set of 1 million pixels to describe, can I reduce this image to only a few key points that describe the rest of it? And these sort of compression functions that you're trying to learn, say taking a function or a data point and be able to map it back to itself as a form of compression. Take the form of tools like principal component analysis, which will be in one of your example notebooks, as well as autoencoders, which I imagine we'll be covering in some of our later tutorials as part of this series. Now, as I mentioned, what we're going to talk about today is just one of these very many categories of learning, and many of which that you're going to learn in the tutorial series. I don't even have captured here. Like I believe we have a segment on reinforcement learning. So as I alluded to, the real kind of challenge that we're going to tackle today is the supervised learning problem, where, as I mentioned, supervised learning is a technique in machine learning where we're trying to model functions that, given some input, predict outputs. Now, these functions could be classification functions, where I'm trying to label one of a finite set of possible options. And these could be, say, simple things like, given an image, to identify whether it contains a hot dog or not, or other kinds of classification that are, say, used in a more nuanced manner, such as classification or segmentation problems, where perhaps I can take an image of a lung and I take each individual pixel and I classify whether it belongs to, say, different features within the lung or not. We're here in the particular examples of classification that I choose. The function that I'm trying to model is, what would a human classify this image as? There are also regression problems that instead of modeling from a discrete set of choices, you're trying to predict a continuous value, such as perhaps what is the probability that an engineering student is going to go to grad school. It turns out that the unemployment rate is a very good predictor of that. And additionally, there are also forms of regression that, like our classification example, are hidden in the way that they're used by a larger piece of software. Google nowadays uses neural networks to be able to predict travel times. And they can take features like what is the time of day and be able to infer how long your travel time would be, presumably by predicting the travel time on many individual segments within that route. So now that you've got an idea about what are the possibilities within supervised learning and what it is that you're trying to do, we'll start to talk about the specific algorithms that you use. And again, I'm going to start here with the linear regression example, because it actually captures a lot of the key behavior or the key concepts within machine learning that you'll need to understand larger algorithms. Now, if I'm to take our familiar y equals mx plus b form, I could say that this mx plus b defines the model architecture. It defines how the computations are going to be performed given a new piece of data. I'm going to multiply it by one weight, then I'm going to add it to the other. Incidentally, m and b are exactly those weights. Now, once I have this machine learning architecture, its objective function or loss function is to be able to find a m and b that minimize the error from the training data. Now, incidentally, the way that I go about making this better is very straightforward. For linear regression, there's actually an analytical solution that if I just compute the covariance between my x and y and divide it by the variance in x, I can get my slope weight, and that allows me to compute the offset b relatively easily. So here you've got it. Just to recap, we've got a machine learning algorithm whose objective function is to minimize discrepancy with the training data, and it produces a model with an architecture defined by a multiplication and an addition function, whose weights are determined by an analytical solution. Now, taking one step forward, we can look at linear regression's cousin called logistic regression, which is used for classification. Now, what logistic regression does is it takes that linear model mx plus b and it puts it through a logistic function such that instead of predicting a value that ranges continuously between negative infinity and positive infinity. We instead have a function that predicts only between 0 and 1. And this we can interpret as a probability. So here, looking at our model again and speaking in those abstract terms, we have a model architecture defined by that multiplication and addition, but with some additional complexity on top of it in order to make it look like a classification model. Once I have that bit of model or software, if I'm going to speak even more broadly, I have an algorithm which makes it better at classification by minimizing this so-called log loss function, which is taking the discrepancy between my input data and the predictions of the machine learning probability. And here, there's no exact solution for being able to solve logistic regression. That is, given some certain observations, be able to find the M and B that makes the best model. So instead, I use this iterative solver using a technique called gradient descent, where I start with an initial guess for M and B, then I identify which changes to them will improve my model. I make those slight changes, then I repeat the process until I find an M and B that optimizes my loss function. So this is called gradient descent. You're definitely going to be seeing this again when we talk about deep learning, for the fact that these algorithms are the underlying of many neural network techniques. But hopefully it shows you in gradually increasing complexity how these different kinds of machine learning functions operate. Now, as I said in one of our early parts of the lecture, this would be a very short class if linear models were the only way for being able to create machine learning models. And this is not the case because not all data are described by simple linear functions. If I look at regression and classification, I could perhaps have data that has a parabolic relationship or a regression problem that has this two different decision surfaces where I can't model either of these problems effectively using a linear model. Now, going on from there, you could think, well, one simple algorithm would be instead of modeling this with a linear function, I allow it to have polynomial terms, but this starts to get into an area of machine learning that's really where the largest amount of work for the data scientist is. And that is being able to find how I add the complexity in such a way that I can fit to my data better than I did previously, so avoiding the so-called underfitting problem, but not ending up with these kind of unphysical parts in your model where perhaps if I fit with this linear regression or polynomial regression model, I have this very large fluctuation at the end that probably is not realistic. So being able to answer questions or being able to model more complex cases and data involves solving two different problems. One, how can I learn more complicated functions? And how can I do that in a way that avoids this problem with overfitting? And there have been numerous ways of solving this problem in the several decades that machine learning has been studied. And one good way of being able to see this is looking at just the zoo of machine learning algorithms that are available in different software libraries. If I'm looking at Weka, which is a tool based in Java, one I used a lot during my PhD, you can see that there are many different broad categories. There are Bayesian methods that use Bayes' theorem to be able to create accurate models. There's many different flavors of linear regression. There are k-nearest neighbor models, and not just one, but many different kinds of decision trees where I realized my colors of my arrows didn't come out here very well. But decision trees are a completely different class of models than our linear regression, where instead of having a simple deterministic function, we have one where we gradually answer a more complicated series of decision rules to identify what the output of the function is. And within these very many different ways, there are many different types of decision trees. There are many different ways of deciding what these rules are, what values to place on the leaves at the end of the decision trees, whether you need to remove rules later after fitting it in order to avoid overfitting, and many where forward. Now, our goal is in this lecture isn't to teach you all of these methods, of course. What we're going to do in the next couple slides is talk through a few of the basics of these. Then we're going to go into Scikit-Learn to show you really how you choose between these different methods and test them out for different algorithms. And the one thing that I realized I had an animation here to pop up is another thing to take from the fact that there are so many different machine learning models is and I will wager money on, there will never be a single machine learning algorithm that works best for any problem. So one of your key bits of work in using machine learning is going to be able to choose between these different spaces of possible options and be able to evaluate them effectively. So as I mentioned, just to get a little bit more into complexity, within machine learning or linear regression models, there are actually quite a bit of variation. And one of the key classes of linear models that are good to understand are those that are penalized by adding another term into that fitness function. We remember from earlier, our objective in fitting linear regression is to be able to minimize the difference between your predictions and the data set. And with the addition of this penalty term, our loss function also penalizes us based on our complexity of the machine learning model, where alpha defines our weight, and this double bracket notation defines some kind of sum over all of those parameters, where depending on our choice of this value for P, we can get different behaviors for the penalty. I could say pick this so-called L1 norm where I choose 1 for this option so that my penalty becomes just summing the value of these coefficients. I end up with what's called a sparse linear regression model because very small introductions of a parameter lead to a moderate penalty, which results, interestingly, in when I solve this equation, when I find my set of parameters that minimize my difference to the training set and my complexity loss, I find that many of them must be 0, which gives me a relatively simple model. There are also other kinds of models, some of which we'll be using today in our kernel methods example, called ridge regression, where we choose 2 for this value, which means I sum the squares. And this means I have a very small penalty. So I get a more complicated model. And these linear regression models are still used a lot because they're, 1, particularly quick to train. If I choose 2 for the value of this penalty, there's an analytic solution, which means I can solve it very quickly. And because these are linear models, I can easily understand their behavior, especially if I choose 1 for the value of P, and I get a model that has very many terms that are 0, and I don't need to understand their complexity or their influence on the model. And of course, as we discussed earlier, there's a limited amount of complexity that you can express with a linear model. So that may be one reason that you need to go on and choose a more complicated model form, perhaps like a decision tree, okay, there we go. Sorry, my PowerPoint was frozen. Which decision trees allow us, as we described earlier, to learn a series of rules. And we do this using a very different kind of approach than with linear regression, where my goal is to solve that simple loss function by adjusting the weights of my model such that they minimize it. Instead, with decision trees, I find that the best way, or one finds that the best way to solve it is using the so-called recursive approach, where I say, start with my data, and let's assume I want to break it into 2 different regions based on whether it's a square or a circle. I can first go through and check with a perhaps one mathematical approach if I need to make a split in this data or if it's already grouped enough. Let's say it isn't. Then I can employ an algorithm that determines where the optimal split location would be, such as by, say, finding the point that divides these two regions into the greatest concentration of one type or another. I then split the data into two chunks and repeat the process. Say I take this square-rich region, I then find that, well, the proportion of squares is already high enough. I don't need to do it. Perhaps it's the same for the circle-rich region. And now I've created a simple program that I first check whether I'm on one side of a split or another in order to predict whether an instance will be a circle or a square. That's a very simple algorithm. You'll note that I kind of briefly alluded to what the actual mathematics for determining a split or whether that split needs to happen. So you can imagine that given that very broad terms, there are a lot of different approaches one could take to solving them mathematically. And indeed, there are very many types of decision trees out there. And one advantage that choosing one of them would give you over, say, another technique like linear regression is that they're very fast to train. This recursive splitting process means that your training time increases with the logarithm or n times the logarithm of the number of data points, which actually scales slowly compared to some other methods. So you can train it on a very large data set. And even though it isn't as interpretable perhaps as a linear model where I can point to a specific term and ask, does this make my classification more or less likely for a certain outcome? Decision trees still allow you to be able to make those determinations. So at this point, the next question that you have is, once you have these models, how do you go about identifying which one is better? And in particular, how do you go about adjusting any of those fine parameters within the model? And one simple way to understand this is, again, to look at the, say, fitting a polynomial regression model, where this image I show you here shows two different models where I've chosen a different degree of polynomial. And what I've done is I fit them to the points that are covered in circles. And then I've gone on and evaluated the error both on those points I used to train the model, but also some that I withheld from the training process to use to modify the models, or to use to measure the model's performance. So what I can look at is, how does the fitness to my training data change as perhaps I increase one of my parameters, the number of degrees I allow in the polynomial. So you can see here that as I add more terms, my fitness to the training data, of course, gets continually better. But I find also that as I increase the number of terms, my error on this test set actually increases dramatically. So what you're seeing here is a technique known through the machine learning community as hyperparameter optimization, where I took one of my parameters that defines not the individual weights of the model, but something that controls how that machine learning algorithm works, and I adjusted it such that it performs better on a particular task. Now that task here is called cross-validation, because I'm using some of my original data set to validate the machine learning model. And this particular technique is something that you can use throughout a broad variety of machine learning models. And in general, these algorithms are these ways of addressing the change in complexity, what hyperparameter you use, often take the form of two different kind of strategies. One, like we just showed in this example, is limiting the amount of complexity available to a model, perhaps by eliminating terms that are high orders in a polynomial, or by adding a penalty function like we discussed in those penalized or regularized regressions that penalize a model from learning too much complexity. such that now you get a trade-off between model accuracy and model complexity. And once you have that ability to tune your models, the way that you do that is to perform cross-validation, as how we demonstrated in that example. I take my data, I set aside some of it from being able to use to train the machine learning algorithm, and use the other to be able to identify how well it performs. And there are many techniques for this. There's techniques like shuffle split, where I divide data randomly by percentage. I train on one larger chunk and I test on another. Or there are techniques like leave one out, where I take one specific data point, I remove that, I train on all that remained, I test on that one remaining point, and then I repeat, picking a different point until I gradually iterate through the whole data set. And once you have this ability to both adjust parameters of the machine learning model, be able to test how well that affects your model's ability to generalize through cross-validation, the process for iterating through that choose parameter and test it is called hyperparameter optimization. And one of our notebooks today is going to teach you how to do that with Scikit-Learn. So at this point, this actually wraps up the me talking through slides portion of the first half of our class. And before I go to the Scikit-Learn, I just want to remind you of all the different bits of theory that we covered. In general, the way that I view machine learning, and a way of view that is shared by many others, is that machine learning are those algorithms which generate software that produce desired outcomes. And this broad technique has very many different subcategories that are each different in what is that desired outcome, how do I achieve it, and what sort of training data does that require? Where, for example, supervised learning finds a function that predicts y given x. And there are many different ways of solving even just a general area like supervised learning, because each have their own advantages and drawbacks. You'll be learning kernel methods today, which, unlike decision trees, which scale very slowly in their time to train with the amount of training data, actually do so very steeply. The training time increases with the cube of the number of data points you have. And then finally, the last bit of machine learning that you need to understand is that each of these learning algorithms will have parameters that control their complexity, and you must find that delicate balance between too simple of a model to learn from your data and too complex of a model to be able to generalize. And as an example, one way to think about that is how many terms do you want to add to a polynomial or not? So at this point, we'll switch over to doing some practice examples with Scikit-Learn. And at this point, I'm going to jump over to Jupyter Lab and give you guys a few moments to get Jupyter open so that you can follow along with me, and give me a chance to top up my water so my voice doesn't cut out during the later part. So at this point, I'll get you started with knowing where to look. If you cloned our AI science training series in the beginning of our research, or in our tutorial next week, you'll see that we've added a machine learning segment that contains two different parts. There's an introduction to Scikit-Learn and a introduction to machine learning with scientific data. We'll be going through part one at this point. And let's say, Elio, would 4 or 5 minutes be sufficient for people to jump over?
Yes, I think there will be plenty of time.
All right, I'll be back to help. I'm just going to get some more water to help out my voice before I help make sure people get Jupyter Lab working. 1 second. All right, so hopefully you're all seeing Jupyter Hub. All right, so I'll point out a few things before you guys get started. The one is that We have some special instructions for being able to run the notebooks in especially part 2. We've got a special kernel, which kernels in the Jupyter parlance are what software environment runs the commands to put in your notebook. And we have a special one called Rapids 21.10, which has the packages that we need for our particular examples. Now, in Jupyter, there's a button for kernel up at the top that if you go to chains, you'll be able to see you can have a number of different types of kernels. And the one that we want here is Rapids 21.10. So once you select that, you'll note it's now started up a different kernel for me. Another side note is my screen's going to look a little bit different than yours. For purposes of keeping me in an environment that I'm comfortable with, I'm running mine off the Jupyter Lab server running on Theta, just so I also don't get booted in between starting the lecture. By booted, my allocation on one of the nodes on Theta G doesn't get removed during a lecture. So that's to save us from that. But during the beginning part of the lecture, we're not going to need a GPU. So a side note, I am a huge fan of Jupyter. So and actually, in fact, use it for all of my projects here at ALCF. And we can, you can access the file system and be able to say, pull out quick summaries of how all of your runs are doing. It's something that I use in my daily life in research as a scientist, and lets me create notebooks that I can easily explain my science with others. So I'm a huge fan of it, love it for teaching. And if data science is something that you're considering for your career or to get more into, I really encourage you guys to work with Jupyter. So I know that was unsolicited part of the curriculum, but like I said, I'm particularly passionate about using it for teaching and research. All right, so that sidetrack aside, well, let's get started with learning about Scikit-Learn. I'm just going to check to make sure there was nothing particularly on fire in the Slack channel. All right, so Scikit-Learn is probably the most widely used tool for performing what's known as conventional, or at least the term I use, to describe the kinds of machine learning that are not neural networks. And as we'll see over the next couple courses, it's got a variety of tools that cover many different kinds of machine learning algorithms, both in fact the supervised learning that we're going to be talking about today, but also dimensionality reduction and unsupervised learning like clustering that are important across many areas of scientific research. Additionally, along with that, there are a lot of tricks in Scikit-Learn that make it possible to create models that are very easy to use, easy to tune to ensure that they're performing the best and not over or underfitting to your data. And those are going to be the kind of things that we'll focus on during our lectures today. So I'll start off with this notebook by loading in some of our data. I'm also going to set a random seed such that I'll get the same output each time. And we'll get started by, again, going back to our friend linear regression. So the way that all machine learning models and basically all tools within Scikit-Learn are built is that they're built on top of this base estimator class, which when you create a base estimator object in Scikit-Learn, it comes packaged with a lot of functions that allow it to work well with other parts of the Scikit-Learn infrastructure. And to create one, you start off by making an object with Python. So here I've instantiated or created a specific instance of a linear regression type object. And we can note that how this particular creation function comes in with a lot of different options that define how you want to create a machine learning model. For instance, you can control whether to fit an intercept or not, which I have set to be true by default, but I can also change it to false. And I'm changing a specific attribute of this object. One of the cool things about Scikit-Learn, which allows a lot of their tools to be integrated together, is each of these base estimators has a get and set params function that allow you to be able to look up all of the possible options at any point. I can see here, there is fit intercept, and I can also see that I've set it to false, but I can then go through and change it through another similar simple interface. So for all of these options, I can quickly see, or for all of these different types of objects, I can quickly see what are the different hyperparameters I can adjust. Additionally, every one of their machine learning models also follows another very common pattern for being able to fit it and run predictions. So here, I'm going to start off by creating some initial random data that I create using NumPy. I create a series of functions between, or a series of numbers between 0 and 10, and I've created it to be a two-dimensional array that has a certain number of points and one column. I then take those functions and I'm going to create a linear model, and I'm going to add some random noise to it just to make this learning problem a little more interesting. So now that I have this model, well, this data, I'm going to print it out and fit a machine learning model to it. So as I mentioned, all machine learning models in Scikit-Learn follow the same behavior. They have a fit function, which in the case of supervised learning, takes the X's and the Y's. Now, once I run this fit operation, it has changed my object such that it now contains the weights that I learned from the model. I can see here, I've learned a set of coefficients that have a value of about 2. You can see it's 1.94, and that's close to the answer that I know to be the ground truth when I created the data. Once I have this model, I'm going to create a set of points to run it against. Here, I'm creating a set of equally spaced points between 0 and 10. In this notation in NumPy, what it does is it takes my 1D array and makes it two-dimensional, such that my XCval is now a matrix that has shape 32 by 1. Again, Scikit-Learn expects all of my input arrays to be two-dimensional for the X's. So once I have that, I can call the predict function to be a broken record. Every machine learning model in Scikit-Learn has a predict function. And I can take that and run it across my initial points. And excellent. Now I have a machine learning model that predicts y equals x, and it does so decently accurately. Now, we're going to stop and give you a chance to try this out for yourself. We're going to give you 5 minutes, so until it'll be 4 o'clock Central Time, to be able to implement a linear regression model, but I want you to do it without a fitting an intercept. Once you fit that model, make some predictions on that XCval variable that I have, and name the model that you fit LR2 and the predictions y pred equals 2. Now I'll give you 5 minutes to do this, but I don't want anyone to get caught up stuck at an old part before I get to the later parts in the notebook. So if you want, the answer is actually hidden in the cell below. So again, we'll give you guys a couple minutes to be able to create and fit those models. Then I'll go back and we're going to move through some other parts. So I'm going to hang out on the Slack to see if anyone has questions. All right, Kyle is way faster than I am, so I'm gonna wait around and see if there's anywhere else I can help out with. Good question, Darcy. So the intercept is actually stored in a different variable. If I take a look at my linear regression model, and here I just put out help, we'll see intercept is actually a different variable within the outputs. So if I wanted to access it, and we can see that it's in fact close to 1. There we are. The intercept's 1.38. No, thanks for the question. So another Jupyter trick that you guys might want to know is if I have a function like the one that creates a linear regression model, I can hit Shift and then Tab, and it'll bring up all of the options that I can see. So just a nice little shortcut. I actually missed last week's lecture. Did we cover a little bit of Jupyter on that?
No, not really. Just a Jupyter Hub.
Okay, so yeah, I'll keep dropping Jupyter facts as we go then. And glad to know that it isn't completely unasked for. But I'll try to stay quiet while you guys work on this segment. And wow, does Kyle type fast? All right, so one other special thing I do with Jupyter is we're not directly teaching Matplotlib in the lecture today, but it's another Python library that's a huge thing to learn, or by huge thing to learn, it will be very important for you to pick up if you do a lot of data science in Python. And it's integrated with Jupyter, such that if I put this little magic command up here, matplotlib inline, whenever I make a plot in MATLAB or in Matplotlib, it renders it inside of my notebook. And I like to make them using this syntax, plt.subplots. Different tutorials you'll see on Matplotlib will do it slightly different ways. Sidebar on the left. Oh, so yeah, Tetsu. So I'm using a special version of Jupyter, one that I'm really comfortable with working in, called Jupyter Lab. It puts everything in one browser tab. So a lot of the things that you'd see in multiple tabs are here. So the way that you get to that on ALCF is being able to go to the jupyter.alcf.nal.gov, and then if you put a /lab at the end, it'll get you there. I don't know if that works on Theta GPU, so I might have just introduced too much trouble than it was worth, but that's one way I get to this interface, which I find more convenient.
I believe Filippo posted a link for how you can get to the Jupyter Lab interface.
Oh, excellent. Yeah, it's one, I like it. It cuts down on the number of tabs that I have open. All right, as promised, I'm gonna go and move on from here. All of these notebooks will be available later, so you can try to answer the questions on your own. But for being able to move through, I'm going to go ahead and paste in my answer today. So you can see the way I did this was when I created that model, I set the intercept to be false at the beginning. I then fit it using the fit command and run it using predict. So I now have a machine learning model. It looks like I forgot to put the legend on this chart, but we can see my intercept and no intercept models look actually both fairly reasonable for this data. So our question will become, how do we determine which one actually fit the data better? And to do that, we're going to use Scikit-Learn's metrics library. So the metrics module, which comes packaged with Scikit-Learn, holds many different ways for modeling the performance of different machine learning models. For example, I can take the points that I have from the predictions of my machine learning model and compute the mean absolute error, where what I do is I compute the differences between true and predicted for each value, and then I average their absolute values. So that's mean absolute error. And if I look through here, I can see that my machine learning model gets an error of about 0.9 if I include the intercept, and it's worse. It fits the data less well if I don't include that intercept term. So another quick thing that we're going to do before moving on to a more complete topic is I'll give you another 2 minutes to, instead of computing the mean absolute error, to look through and calculate the mean squared error between two data sets. And the one thing that I'll show you is the way that you work with this module is if you type out metrics and hit tab. Okay, well, it actually doesn't work here, but if we type help metrics, it'll show us all of the different functions that it has built in it. It's going to be a lot, so we can search through it with the text. And we can find here. Unfortunately, I didn't paste the link to also go through the website, but if you look through Google, you might also get to the answer that you need. All right, so we'll give one more minute. All right, excellent. So this one, relatively straightforward. Instead of calling the mean absolute error function, I just call the mean squared. And you can see Scikit-Learn gives me that ability to make a different kind of qualification metric. All right, so the next part we're going to teach in Scikit-Learn is their pipeline functionality. So what we're going to demonstrate is how building a complex model, like a linear regression model that has polynomial terms, can be tedious, but using pipelines so that you combine many different parts of a model into a single package such that later you can forget about how to run that machine learning model because it will all be behind Scikit-Learn's easy fit and predict relationship. So let's start out first by creating another example problem. Here, I'm going to use NumPy again to create a polynomial model with some random data on it. And you'll see here, fitting and predicting on my linear model doesn't work very well. So what I really like to do is be able to take my data, first expand it such that I include polynomial terms, and then use linear regression to fit a model that includes those polynomial terms. So first, let's do that in 2 steps. What I'm going to do is take this so-called transformer from Scikit-Learn. It has a pre-processing module that contains a lot of useful tools, like one that will take my input data and expand it such that it contains polynomial terms. So let's do that. I'm going to create a polynomial features. I set it to have degree 3. You can see here, as I said, it's a base estimator, so it has get params. And it also has a fit function, just like everything else. Here, the fitting actually just tells polynomial features how many inputs to expect. And you can see that here. You'll note again, the attribute has a postfix with an underscore on it to mark it as something that's learned through fitting. And then once I have it, because this is not a machine learning model, it's something that transforms data. Instead of having predict, it has transform. And if I were to run my input array through it to create polynomial features, you'll see that the first row of that output array contains my original number, that number squared, and then that number cubed. So awesome. We've now got a component to our machine learning model that can take our data and input data, transform it into a way that'll make it easier to learn. So here, let's take that input data. Now let's fit it again. I'll note here, you'll note I'm using the same linear regression model over again. And that's because as soon as I fit the model, it throws out the old weights and learns new ones. So I don't have to create a new copy. I can just overwrite my old one, which I'm doing for convenience. So now I've got a fit model. So in order to make predictions, I need to take my data, first compute the transform, then compute the prediction, and nice. I now have a nonlinear polynomial model, but one that's kind of annoying to run because I have to keep track of 2 variables and I have to know the order in which I run them and what function to call in each of them. And that just will make any resultant software I create using this machine learning model more complex than it needs to be. Instead, as I told you earlier, what I can do is I can create a pipeline model that takes these 2 steps and always runs them in sequential order. So what I can do is, or to create one of those, I define a pipeline object where I give it input data that first, that includes my polynomial features. And you'll note the way I provide it is I give it a name, the step a name, and then the object that defines that step. And I do that for both polynomial regression and linear regression. And if we run this cell, and if I type PR, yep, you'll see I've created a 2-step model that goes polynomial expansion, linear regression. Because it's a Scikit-Learn base estimator, I can set its parameters using the set params function and look to make sure they were set correctly with the get parameters. Now, in order to train this machine learning model, I can call a fit and predict function. I don't have to know those separate steps. And to my great relief, I can create this cubic model without so many problems. Now, at this point, we're going to transition to an exercise that we're going to give you a few minutes to work on, kind of under the kind of close watch of me and my ALCF colleagues, but will be something that I'll encourage you to do after the lecture today to make sure you can be able to work comfortably with a pipeline model, be able to fit it and run machine learning models and test their accuracy. So what we're going to do here is I'm first going to grab another utility function from Scikit-Learn called train test split, which if I give it a list of arrays and some information on how I want to split them, we'll create separate copies of those arrays divided into a training and a test set, where when I run this, I create a version of xtrain that has the same rows as corresponding to entries in ytrain, and same for my validation sets. And you can see now, because I've split it a test set that was a quarter of my data. I now have a training set that has 24 points and a validation that has 8. So the exercise that I want you to start, and as promised, I give an answer below, is to fill in the bits of this loop. I want you to change my pipeline model to be a polynomial of a certain degree, fit it, then evaluate its performance on both training data and validation data. Then I've got code that will store that in an array and dump that in a data frame to make plotting easier later. So at this point, I'll let's give you guys another 5 minutes to work on this. Again, to start it off with today, but hopefully this will give you a step towards being able to do this on your own after the tutorial. And can I get a thumbs up in Zoom if people are kind of successfully moving through the different bits of these examples? All right, excellent. Yeah, and again, if you are having problems, don't worry. I just put some answers in the, or put some questions in the chat either today, or I'm sure at least some of us will be watching this after the tutorial and we'll be able to help you through. And if not, I do have the answer for you to work backwards from. But we'll wait till 15 of the hour, and then I'm going to move through. All right, so especially since we're not seeing many questions, I'll go ahead and punch forward. So what you'll see for our answer, which I'm going to just copy into the array, is what we end up finding, and it worked out really well with this example, is you'll see that, well, once I add in the legend, you go and update my GitHub to show it, is that if I look at my training error, it gets continually lower. The more complex model, the better it can fit the training data. but it does so at expense of my validation error becoming huge, in that the model doesn't do very well on data that it wasn't predicted with, or that it wasn't trained with, because that model was overfit to the data. Now, our next notebook is going to actually go into how you can do this kind of hyperparameter optimization more efficiently in Scikit-Learn. So I'm going to close out of this notebook, and we're going to move into the next one, which is titled 1, Kernel Methods. And I'm going to teach you here not just a kind of a really cool type of machine learning, at least I find it very kind of intellectually satisfying, but also one that if you use, you have to be very adept with using hyperparameter optimizations. And that type of machine learning algorithm is the kernel method, or a kernel-based approach. So let's load in some examples. And then we're going to go through a bit of examples on kernel methods. So kernel methods arrive in a way, or they're based on this concept known as the kernel trick, where you transform your data in such a way that it makes your machine learning problem easier to run. Now, this kernel trick can be something simple like a polynomial expansion that we showed is in some ways a kernel trick, but there's some pretty clever things you can do with these techniques called radial basis function kernels. So to exemplify that, we'll take a classification example where I've got some points that I want to classify between light and dark, that, as you see here, as currently displayed, I have to create 2 decision surfaces to break them into 2 categories, which isn't ideal because there are only 5 data points. This is a very complicated model for such little data. What kernel methods allow me to do is take this initial data point and create a new set of inputs that could perhaps be easier to learn on. So the trick with the so-called radial basis function kernels, and all kernels in general, is I create a new set of features where I'm going to bump up the font size. Unfortunately, I've got math on this slide. That is a little hard to see. Okay, that wasn't what I wanted. Here we go, a little bit bigger. So what I'm doing is I'm creating a new set of features, K, that are based off applying this pairwise function over all pairs of initial inputs that I provided. So effectively, I'm calculating this kind of similarity between my input data points, and using that similarity between each of my input points as a new feature. Now, it happens if I compute this feature matrix, and we'll see this feature matrix is 5 by 5. I have 5 training points. So I have 5 different rows in this matrix. Each column is a feature I'm using as an input, and I have 1 feature that's the similarity to each of my inputs. Now, if I take a look at one particular feature, if I look at number 2, I can see that if I now look at this space, my points, according to feature 2, can be split using only 1 decision. So this is great. I've done no kind of an increase in complexity of my machine learning model. I've just messed with my data a little bit, and now I've got a simpler machine learning problem. And this is a kind of machine learning you'll see many different places in the sciences. It's particularly popular in chemistry. There are some really cleverly designed kernel functions that capture physics. We're not going to touch those today. But if you're interested, ping me on Slack, and I have a whole nother lecture on that, which I'd be happy to send you a recording of. So along with this kernel method for classification problems, you can also do it for regression, where the idea is I create a regression model where I multiply each of my new kernel features by some coefficient, and which effectively is a linear regression model. I multiply my coefficient by one of my new features. Because of this linear regression, I can use this penalization or regularization term. And one thing that one commonly does with kernel methods is you choose 2 for the norm, which means you can get an analytic solution to solving what the C's should be. And you can do it very quickly thanks to some clever mathematics. So let's show you how to build one of those in Scikit-Learn. Scikit-Learn has a kernel regression, ridge regression model built in, and we're going to create it using the radial basis function. And you can see here that besides the choice of the kernel, you have a few other parameters to pick between. Namely, you have the alpha, which I'll go back up to this equation. That's my strength of the weight for my penalty of having too big of features. And secondly, I have another one to point out called this gamma here, which controls the width of the kernel. You can see it here in my radial basis kernel function. Now, to actually explain what those mean, we'll take a look at some pictures. So I'm going to create some initial data of a quadratic function, and let's see what happens with different choices of my width. Now, my width of the kernel defines how sharp the different features in my outcoming model are. And you can see if I pick a small value, they're very diffuse. And if I pick a larger value, I get very sharp derivatives in my output function, which in some cases could be good, but you can see here, it's probably this 0.1 figure that I want. I can get a different kind of behavior with my alpha. My alpha controls how well I adhere to the training set because it's, again, it's that penalty function for complexity. And if I choose a very low penalty, I fit the training data very well. If not, I don't, at the expense of having a model that's, or at the benefit of having a model that's simpler, that is flatter. So as you may guess, just like our polynomial example model, our challenge in using ridge regression is to find the right alpha and the right gamma for our particular problem. Now, a simple way to do that, rather than write that custom for loop that I am having you do in that other exercise, is to use a tool called Grid Search CV, which Grid Search CV works by being given a model that you want to tune with some settings in it that you want to remain as defaults. Then a list of parameters which you want to vary. Say, perhaps, I want to vary my alpha parameter, and I give it that parameter name along with a list of parameters over which I want to vary. So here, I'm going to say vary between 10 to the negative 8 and 10 to the 0 in 32 different steps. That's what log space does for me. I then give it a scheme for performing my validation. Here I say I want a shuffle split, which is removing 25% of my data for a test set, and it will do that 10 times, and score it via the mean absolute error. The neg prefix means we're using the negative of the mean absolute error because this class is going to try to maximize this score function. All right, so let's create Grid Search CV, and I'm going to harp again. Scikit-Learn, every machine learning model has the same interface. So here, all I do is call fit, and you'll note it has gone and fit the model. You can see here all the parameters I gave it. And one thing that's cool is I can look at the results of the fitting. Here, if I take a look at the parameter or the CV results attribute, again, underscore means this is something that's produced during training. I can see that my mean absolute error over time hits a maximum somewhere around 10 to the negative, actually 0.3. Interesting. I get a different value than when I ran earlier. So apparently it must be a different random seed. But the point
I think the random state is also changed, perhaps.
Yeah, that's what I'm thinking. We'll pick a different number, and just to illustrate the point, maybe not to illustrate that my initial example was right, we're going to go ahead and rerun the whole notebook just to show you guys the effect of randomness.
This is pointed out in Slack that the random state parameter, a few cells up, the comment says it should be 10, but it's set to 1.
Oh, so this here, it's actually right that it's set 1. What I didn't do in this example, and where the 10 comes in, is the first setting for shuffle split is the number of splits. I've left it on the default So that's what's going on here. So if I we'll just do it explicitly. But yeah, so this random seed wasn't necessarily the problem. The secret sauce apparently was the choice of the random seed for the whole notebook. So now we get a much more dramatic change just by the nature. These choice of points looks a little bit different as a result of changing that random seed. And you can see there's a really big change as a result of changing my complexity parameter. So now that I've shown you that, we're gonna give you guys another exercise for 5 minutes where I have you, instead of changing only the alpha parameter, go ahead and vary both the alpha and the gamma. Change the alpha such that it only does 16 steps, and allow the gamma to vary between -10 to the -4 and 10 in 16 steps. So we'll give you 4 minutes so that we'll round out at 30 of the hour. And of course, let us know on Slack if you have any problems. And I'll see if there's anything that
what was
I
the
left
new
over
seed
from
that
last time. Oh,
the new
good
seed
question.
you used for reproducibility?
2. Yeah, thanks, Kyle. Yeah, so if you want to use the same result as me, just go to 2, then click Kernel, restart and run all cells, and it will go and make sure everything runs through reproducibly. So we can go all the way down to the bottom, and we'll see same shape here, optimal parameter somewhere in the ballpark of -10 to the -3. So do they still teach a lot of MATLAB in undergraduate and graduate courses? Yeah, because if so, one resource that I'll point to you guys, I realize I use a lot of NumPy shortcuts. If you want to learn that and how to do NumPy and you already know MATLAB, if you search NumPy for MATLAB users, you'll see a translation for a lot of the functions that you might see me using here. And it's a quick way, it's how I switched over from using MATLAB to NumPy. Yeah, I was on the fence on whether to use a lot of these NumPy shortcuts, opted for it to give you guys exposure to how easy things can be once you get familiar with the tools. Yeah, that's interesting. Yeah, when I was an undergrad, which actually wasn't a whole long ago, the NumPy wasn't as well developed. So hopefully they'll switch over to that. I happen to be a big Python fan, but I suppose MATLAB has its good things about it. Yeah, exactly that, Sebastian. But indeed, the principles do matter. I just happen to like free software. But yeah, if I wasn't soapboxing about Jupyter earlier, I will stay off the open source one. All right, so as promised, it's 30 of the hour. We're gonna jump and just show you the answer here. You'll note what I did was I added another parameter to the parameter grid. and then I just call the fit function because it's just another machine learning model. And now I get a really beautiful fit to my data. And now you've seen, learned a little bit about kernel methods, which are a nice, really cool niche application in machine learning. They work exceptionally well for certain classes of problems. And you now know how to use grid search, which will no doubtly come in handy. So at this point, I'm going to switch back from giving the points or giving these practical lectures to going back to a little bit more theory before I set you loose on one of our more complex exercises at the end of the lecture. And also between now and getting you onto that notebook, we'll be giving you an introduction to the Rapids project, which gives you the ability to run a Scikit-Learn-like interface, but with methods backed by GPUs. So the next part of the talk, I want to focus on what are the kind of concepts that allow you to use machine learning for scientific problems. And a lot of this, I'll warn you, is going to come from my background as a materials engineer, also because I teach a course at UChicago on AI for materials science. And a lot of the material here is brought over from that class. So the core challenge that you might run into first with using machine learning on a scientific problem is that not all of your data are already in a good vector format. You might try to build a machine learning model where you predict the property of a molecule or an image, which, while a vector, can be expressed in many better ways. Or it may be a social network or a weather forecast, neither of which have a very clear way of casting them into that array that you pass to a Scikit-Learn model. But this isn't something to worry about. There's still many approaches to be able to use machine learning with different kinds of data. In fact, any kind of scientific data, I'd argue. So one way to think about being able to create machine learning models that work on scientific data is being able to transform the data into a representation that captures the knowledge that you would use as a scientist to be able to solve a particular challenge. Now, the one I'll give you, again, is borrowed from materials engineering. And this would be, how do I predict what a crystal will look like, given some information about it, perhaps its composition, say sodium chloride. Now, as someone with a background in inorganic chemistry, I could look at this material and say, well, it's got a high difference in electronegativity, which means it's going to be strongly polar, have a large band gap. Because it has a large band gap, it's not going to interact with visible light, which means it's going to be clear. Additionally, I know something about crystal chemistry, and I'd say that sodium and chlorine are about the same size, which mean they're going to pack to have a coordination number of 6, which leads to cubic symmetry, which means it's going to be a cubic crystal, and voila, sodium chloride is actually a cubic crystal that in its undefected state is clear. So what this is showing you here is the way that you can take a scientific problem and identify features, and I'll get my laser pointer back on, that capture what is it specifically about this bit of data that I can quantify about it in order to make learning a problem possible. I can take this logical leap to be able to build a machine learning model. Now, this more broadly, we can call a representation. And it's a way of, at a high level, developing a set of quantitative attributes that describe some bit of data. And what these properties they need to have is be able to transform this data from something conceptual to a tensor that can be treated by a machine learning algorithm like any other kind of information-rich data. And what makes a really good process is being able to come up with a representation that makes it easy to learn simple generalizable rules. Now, there's a lot of thought on this subject, which I'll give you the high level on. As a side note, my PhD was on this subject, so I have a lot to say about it. But the 4 things I want you to walk away with are ideas that to be able to create a good representation for your data, you want to think about whether that representation is complete. That is, does it take all of your data and ensure that they don't overlap such that the same piece of data is at the same point. It's got to be compact such that you're not describing too many features, but you want those features to be able to be descriptive to capture some key rule about that data. And finally, you want it to be simple to access. You don't want to be able to run a lot of compute. So if I were to take an example of, say, these elemental compositions, and I want to classify them between metallic and non-metallic, if I did so with the fraction of sodium, that would meet 3 of my 4 criteria. It's complete in that it differentiates materials. It's only 1 variable, so it's compact. It's simple. I don't have to really do much complex computation, but it doesn't, it creates a complicated model. Again, many decision surfaces, yet only a few data points. Now, rather, if I went to my chemistry textbook and saw that the difference in electronegativity is what often describes ionic materials, I'd be able to use that as a feature, which is much more descriptive and has all of these other properties. Now, just for a sake of completeness, the different kinds of representations are useful for different problems. Say, if I want to predict the melting temperature of a material, I could use a very complicated calculation like a density functional theory, which takes about an hour to compute for a single type of material, which means if my data set were only 100 points, I could be able to use this as a feature. It would be simple enough, but this would not be okay if I had 100,000 materials. That would be a lot of computing power, so it wouldn't be a good choice. So really, there's not going to be one set of representations that works for all problems. You have to think about what is it that's specific about my training set, how much resources do I have available. So there's a lot of degrees of freedom for you to think about it. Additionally, there's a lot of different kind of schools of thought when it comes to coming up with representations. There's some ideas where I don't necessarily want to capture all of those important features. I want to be able to just differentiate my data such that the machine learning models that I come up with have maximum expressivity. Yet this is something that often results in requiring a lot of data. So while I get the ability to create complex models, I don't, I require a lot of data. So these are the kind of techniques you typically use with deep learning. And you'll see in some of our later lectures, one examples of these kind of descriptive representations is to describe an image by its pixel values. And they've shown that that's a great way for doing facial recognition. In contrast, are these more discriminated? Actually, well, I have these backwards, but there's another class of representations where you try to capture key features that describe your data. Say, for example, if I'm doing facial recognition, the distance between someone's pupils is a pretty good descriptor on being able to separate different people from each other. And while this allows me to learn very simple models for being able to recognize a person, it paints me out from being able to create a very complex model, say with deep learning. So again, this is another variable that you'd want to consider. What kind of model am I going to use? Am I going to go for complexity over simplicity? And some examples that you'll see in chemistry, and incidentally, we're going to use during some of our examples today, are different classes of features, like being able to use a fingerprint, where I search for being able to describe a molecule in a very rich way that allows me to create complex models, such as by describing it with a text string, or say with a binary list that describes whether a particular type of molecular structure, like an oxygen, is present in the molecule or not. And these are different than descriptive features that say capture Well, what is the solvent accessible surface area of the molecule, which is something I can compute very quickly. And there are textbooks that are hundreds of pages long. In fact, you can see here, this handbook has a bibliography that is 130 pages that really capture the kind of breadth of ways that people have thought about describing just one particular kind of data, molecules for machine learning. The other concept I want you to understand, besides that there are many different ways of describing machine learning or data in a way that can work with machine learning, is that you should also practice some care with being able to create machine learning models. Now, at this point, I was originally planning on switching over to practical exercises. I'm actually going to go through the last bits of my slide now so we don't flip back again later. And that bit or bit of knowledge that I want to kind of open your eyes to is that you should really think hard about how to validate a machine learning model. Because while there's some very simple ways for doing cross-validation, you can do a lot better by thinking about the problem that you want to do. And creating these validation strategies often comes in two different parts. The first of which is, how do I split my data into segments that allow me to kind of test real-world applicability? Say, what do I use for my test data as opposed to my training? And then finally, what are the metrics that I use to be able to ensure my machine learning model is working the way I want it? Say, a very simple method for validating a machine learning model's ability to identify road signs is to take images and measure how well does the bounding box capture. But that's hard to translate into the real world. Ideally, you'd want to test these machine learning models in practice, but of course, that's expensive. There is naturally some middle ground you can do by, say, simulating how many road signs that it misses, as an example for a metric that's somewhere between those two. So to start off with giving some background on ways that you can design better validation methods, we'll talk about the k-fold cross-validation, which is kind of the default way of approaching creating a way of partitioning your data. How you do this is I split my data randomly into chunks. I pick one of them to use as a test set. I use a remainder for trained validation. I measure performance of a model trained on the training, on the test data, and then I repeat this using each of my different chunks as my test set, and I report my model performance as an average over all of these iterations. But what this is fine as long as your data is very homogeneous. What often happens in science is that some of your data is, inside of your data set, you often have different clusters of data that are more alike each other than they are others. Now, what happens if you do a random k-fold cross-validation is that each of your training sets will contain types of data that are seen in your test set. So if I want to ask a question like, how well would my model do if I introduced a different type of data? I can't answer that with regular cross-validation because I'm not testing the ability to go from one cluster to another. Instead, one way you can do this cross-validation is to be able to split based on these groups within your data, say train on types 1 through 4, predict on 5. And this will help me better emulate the process of predicting on a new cluster of data, and therefore get a better measurement of how my model might run in practice. And there's some examples of how you might want to do this. Say if you're working with time series data, if I do k-fold cross-validation, I'm actually testing what happens if I do my prediction given data of both the past and the future, which is not ideal. Rather, I'd want to do a cross-validation where I only select entries from the past. Or if I'm doing some kind of combinatorial experiment where I'm varying different variables within different clusters, I'll create a partitioning scheme where I ensure that data from the same cluster is not split between the training and the test set. Very analogous to that, what happens if I have a different type of data question we showed earlier. The next thing I'd encourage you to consider is that there are many different ways of measuring the performance of your model. Now, one question may be, if I'm looking at cross-validation, is it more important for me to, say, not miss a diagnosis? And in that case, I really care about a type 2 or a false negative error. Or am I more concerned about not making false convictions? And in that case, is it the false positive that's my best metric? And this is to just scratch the surface. If I look at classification alone, there are actually many different kinds of ways to describe the performance of your model, that some may be more useful for a scientist who wants to use that model than others. Likewise, for regression, there are a lot of different types of metrics you can use. But one practice that I saw in a paper I was reading recently out of a group at Caltech and Cornell is that they trained a machine learning model to predict this so-called phonon density of states. And what they ended up finding was the model that predicted this density of states the best was not the model that gave you the best derived values from it. So if I actually cared about not predicting the density of states, but that was a means to be able to access something more complicated like the heat capacity, I want to actually measure my model on how well the predictions are how well of a derived value I get from using those predictions. In a similar way to if I were to use this model in a self-driving car, how many stop signs would I miss? This is something very similar and is a very good practice to use, and was something I really thought was excellent when reading this paper. So in conclusion, there are two things that I want you to think about once you can build a machine learning model, and once you're comfortable enough with that, is before you go using it in practice or writing a paper on it, think carefully about how this model would be used in practice and use that to design not only your cross-validation strategy, but also how you would measure its performance such that it will give scientists a useful metric for understanding how good it is. So this wraps up all that I wanted to talk to you about today. As I mentioned, I wanted to give you a breadth on what are all these different algorithms and some depth on how to use a tool like Scikitlearn to use them for science. And then finally give you some examples on what makes scientific data difficult to use with machine learning and how can you overcome those difficulties and then be able to do really useful work with machine learning and science. And those takeaways are, if I were to highlight, to think about really the depth of machine learning models there are to know which one would work well for your problem. And then if you start using some odd scientific data, to think about how you can represent that data and design tests. So at this point, before I go, I'd like to mention that the slides that I posted also have some resources. I particularly like to learn things by reading textbooks. And these are three of the ones that I think are particularly good for machine learning that I might suggest. And one recommendation I haven't tried for myself, but a colleague whose opinion I think is really valuable recently introduced me to this textbook. So I figured to pass it on to you as well. So at this point, I'd like to pass the torch over to Filippo to talk a little bit about the RAPIDS project, and then I'll introduce you to our example problem before we wrap up today. So Filippo, the screen share is yours.
All right, so if you have run the notebooks on Theta GPU using Jupyter Hub, so far you've run all of the computations on the CPU of the node. However, Theta GPU has also GPUs, which are accelerators and allowed to perform computations much faster. So I'll now give you a quick overview of RAPIDS, which is a library from NVIDIA that produces the GPU on Theta GPU that can allow to perform data science and machine learning on GPUs with considerable speed up. So these slides are subset of slides from NVIDIA that you can find on their website, and I'll give you the link later on if you want to know more. This is just a small subset. Rapids aim to speed up the pipeline of data scientists and machine learning modelers. So these typically consist of data preparation. So you have to load the data and then filter, clean, pre-process. Then you go on to model training, where you instantiate a machine learning model and fit it, and then you can visualize the results and test the model. Typical, if you work in Python, typical Python libraries that you use are pandas, NumPy, and Scikit-learn, and then many others that we've seen today as well, like Matplotlib for visualization. So all these run on CPU, and they can be parallelized, for example, using Dask. But if you have a CPU that you can use, then Rapids provide you with a series of libraries that are meant to replace the usual Python libraries that you're used to perform the task. So QDF, for example, replace pandas, QML replace scikit-learn, and those libraries, so those packages aim to basically re-implement the APIs of pandas as scikit-learn as closely as possible to the original CPU version, but they run on GPU, and so they should be much faster. So just to give you an idea of the scale, so you have like operations which include querying your data and transforming your data and then training machine learning, and the length of each segment corresponds pretty much to the time taken, plus you have some read and write operation to the disk or to the memory. What Rapids is able to do is to reduce, in the first instance, the time it takes to perform these operations, because the GPU allows to do most of them in parallel, and then also with a smart utilization of memory allows you to eliminate the GPU to CPU communication for the input and output data. So this produces a considerable speed up. And you have several graphs to see, that what Rapids can do compared to the several tasks over a number of CPUs equivalent. So a quick overview of the Rapids ecosystem is that it allows you to accelerate operations that you usually do on CPU by leveraging the GPU, and this is what we are going to see using Rapids today. So replacing pandas with CuPy and scikit-learn with QML. But also, if you are on a distributed system with multiple GPUs on the same node and multiple nodes, then you can also use Rapids in conjunction with Dask, for example, to scale out and parallelize these operations for even more dramatic speed up. Just a quick overview of two of the libraries. QDF is Rapids replacement for pandas, so working with data frame and processing data. This on the left is a short example of how you can read data from a zip file and then perform some common operations in with the same syntax as Python. And you can see in this graph this GPU speed up over the CPU that you can get over a factor two orders of magnitude, basically, of several operations that you can do on data frame, like merge, sort, or group by. QML is the replacement for Scikit-Learn. So machine learning models, we've seen many. This is an example. So on the left, you have a clustering problem where you want to group points belonging to the same clusters. And this is done on the CPU using Scikit-Learn. Then here, so this is all CPU based, sorry, where you instantiate dbScan algorithm, and then you predict, you get the two clusters. The GPU version, basically, you don't have to change your code except for some import of the models. So here it's QDF, so this replaces pandas, but for the clustering, you simply replace Scikit-Learn cluster with QML, and you get the same result, but this time the model is running on the GPU. So this is kind of the ideal use case where you have some CPU code, and then you just replace Scikit-Learn, for example, with the QML statement, and all the rest of your code should not be changed. It will work on the GPU and much faster. Of course, there are drawbacks that not all of the models and the methods of Scikit-Learn or pandas are currently implemented on Rapids. So we will see an example in the last notebook where you have to choose a different metric because the metric used by Scikit-Learn in that example is not supported, but yeah, that's one of the drawbacks. And again, you have considerable speed ups using the GPU for different clustering algorithms, for example, or other regression models. So if you want to install this, you have instruction at the end of these slides. I'm going quickly because we are almost out of time. So Logan, I'll get back to you for closing the session.
Yeah, thanks, Filippo. And I'm happy to say I learned a lot from getting some exposure to Rapids with working with you and putting it into the course materials. Looking forward to actually trying it out more myself. So I'm going to share screen to show you guys the lectures or the additional exercise that goes on with the lecture today. It's just going to reinforce what we've already taught you with Scikit-Learn, but give you an example on how to do so with, or how to use it with material science data. So this one here, I'm not logged in on a GPU node, so I'm not going to be able to show you the Rapids portion, but I'll at least get you started on understanding how this runs with on the CPU portions. So you note here, I've activated the Rapids kernel, and just to show you, here I've gone into the machine learning section of our GitHub, and you'll see I have two notebooks where each show using different kinds of representations and particularities of working with them in machine learning models. So here I'm going to load in some sample data of different molecule properties. It talks you through how to create the fingerprints, which we use as a descriptor to translate molecule to a fixed length vector. We'll then show you how to do KNN regression and how to build a pipeline model that will take this KNN regression model and be able to combine it with the fingerprint calculation such that you can train a machine learning model with scientific data much easier. And you'll note that we also have some content showing you how much faster it can be with running your machine learning model on the GPU. We'll then show you, and this is going to take a few minutes to run, so the answer won't be immediately here, how changing different bits of your features will affect how your model grows with machine learning, and I'll also show you some tricks along the way with pandas, being able to take data that's from a summary of your experiments and analyze it quickly. The exercise that I encourage you to take a look at actually will teach you how to do feature selection where one takes all of the different fingerprints that describe your molecule, identify only the ones that are the most important for predicting the properties, giving you a faster to evaluate and a more accurate machine learning model. So that'll be an exercise that will actually bring together pipelines, fitting parameters, cross-validation, all together to have you write a rather more complicated example with Scikit-Learn, and hopefully will help you test whether you've got the major concepts for how to use Scikit-Learn. So at this point, I'm going to stop the lecture for today, but hang around for at least a few more minutes to answer questions. And if not, you now see I'll be watching on our Slack. So if you have any questions about this lecture material, I'd be more than happy to answer them later.
Thank you, Logan and Filippo. This was a very useful session, and it is the key introduction, the main bridge to deep learning that we will be covering in detail over the next several months. So if anyone has questions, you know that Slack is open and that you can continue to use Theta G throughout the week. If you want to reproduce these exercises, you are part of the allocation that provides access to this machine. So feel free to go and reproduce what you have been taught today. And if you continue to have questions, you know, we are monitoring the Slack. As a reminder, we have another session next week. Asad Han is going to be providing hands-on materials for that training session. So make sure that you go and review how to use Jupyter Notebooks, explore the use of it using Theta G, and report any issues. Okay. If you still have questions at this time, as Logan said, you can do so here until Kathy says this is enough. We are leaving for the day. And you can also do it over Slack. Thank you, everyone, for being here.
Yeah, thank you all.